Hello everyone. I am Gitanjali Jaina. I'm a PhD student from IIT Delhi. So I welcome you to the live section of the quantum mechanics course, where I will solve some of the problems that will help you to understand the concept of quantum mechanics. Uh, so, last week you have studied about the compatible operators, incompatible operators, as well as Schrodinger picture, Heisenberg picture. So in this lab section, I will solve some of the problems that is related to this concept. And so it's almost time. So let's get started. Okay. So this is the first problem. First, let's go through the problems one. So the first problem talk about two Hermitian operators, anti-commute, and the two operators will have simultaneous eigenstate with eigenvalue A and B. So let's see what is the condition that is given to us. So it is given that two Hermitian operators anti-commute. So similar to the commutation relation, there is also anti-commutation relation of two operators. Let's say we take two operators A and B, and it is given that these are Hermitian operators. That means A is A dagger and B is B dagger. And one of the properties of this Hermitian operator is the eigenvalues of these operators are real. Eigenvalue of these two operators A and B are real. Although these properties are not required for this anti-commutation relation, but you should know these properties because it will help you to solve some other problems. So let's go through what is given to us. So it is given these two operators anti-commute. That means this is the anti-commutation relation. If two operators are given, which is A and B, then anti-commutation relation of this operator is nothing but these are written inside the curly braces, and it is given by AB plus A. So in commutation relation, what you have seen? In commutation relation, you have seen that AB commutation relation is nothing but AB minus BA. So the BA or minus BA is replaced by plus BA in anti-commutation relation. So, and it is given AB equal to AB anti-commute. That means AB is AB anti-commutation is 0. Okay, this is given to us. Now it is asking that these two operators will have simultaneous eigengates with eigenvalue A and B. So it is asking about under what condition these two different operators A and B will have same eigengate. So you know that for two operators, two different operators to have same eigengates, the commutation relation of these two operators should be 0. So what I mean to say is for two operators to have simultaneous eigengates, this condition should be 0. So if they commute with each other, then you can tell that these two operators will have same eigengate. So let's see. So the condition given to us is AB equal to AB anti-commutation relation equal to 0. So let's assume psi is the simultaneous. This is the simultaneous eigengates of A and B. A and B. with eigenvalue a cap small a and small b, small a and small b. So this means that if you add a on side, then you will get the eigenvalue a with the same eigenkit. And if you have the operator b on side, then you will get the eigenvalue b with the same eigenkit. So now let's write this anti-commutation relation in terms of commutation relation. So AB, it is given to you, AB anti-commutation is 0. That means if you have this condition on a non-zero eigenkits, which is simultaneous eigenkits, it should be also 0. So let's open this anti-commutation relation. So this is nothing but AB plus BA acting on psi equal to 0. Now, to represent this condition in terms of anti-commutation, what I will do, I will just add one operator term, which is minus BA, and to cancel it, I will add another operator so that the whole condition is unchanged. So I have added minus BA plus BA, and there is also other operator BA is present there. So this should be 0. Now this you know that it is the commutation relation of AB, and this is 2BA, whole acting on psi equal to 0. So that means just multiply the eigengate with the individual term. This means 2BA psi equal to 0. So you want this term to vanish, means this term to 0. This will only happen when the other term, second term is 0. Now let's see the second term, which is 2BA acting on psi. This is, you know, this is the eigenkits. So this will give A psi. Now when P act on this A psi, then it will give P A psi. So the second term is 2BA psi. So this second term will be 0 when either B equal to 0 or either A equal to 0. So any one condition is fine. So let's see what is the, so when either B equal to 0, either A equal to 0, that means the second term will vanish. And what you are left with is the first term, which is negative psi equal to 0. That means the commutation relation of AB will be 0 when either A equal to 0 or either A equal to 0. So one of the eigenvalue is 0. So let's see what is the option that is given to you. So the first option you then the first option is A is 0 and B is not equal to 0. That means this is the right answer. Okay. So this if two operators anti-commute, then they will also commute with each other when either one of the eigenvalue of this operator is 0. This is the first question. So let's do the second one. So all question that I prepared is based on commutation relation as well as the Heisenberg picture, Schrodinger picture. So that it will help you to understand the concept as well as to solve the assignment. So go through the second question. So let me read out the question for you. This is given for the one-dimensional harmonic oscillator. The position and momentum operator in the Heisenberg picture are given by this expression. So two expressions are given in the Heisenberg picture. One is the, let me write first. So one is the position representation in the Heisenberg picture, which is equal to x0 cos omega t plus ps0 divided by n omega sin omega t, and the other term is the momentum expression, which is ps equal to ps0 cos omega t minus n omega x0 sin omega t. So this is given to you in the Heisenberg picture. So now it is given also this terms. These terms are similar to these are the terms that is present in the Schrodinger picture. Right? X is 0 is x, which is the usual position operator in the Schrodinger picture, and P is 0 equal to pk is the usual momentum operator in the Schrodinger picture. Then it is asking then what is the commutation relation of equal time commutation in the Heisenberg picture. So it is asking about the commutation relation of position and momentum in equal time in Heisenberg picture. So that means what is the value for this commutation relation when the time is same. It's not given, it is asking about what will be this condition. So let's solve. So you can see the first term, the position as well as the momentum terms. Just put the expression in the commutation relation. So one is 0 cos omega t. This P is 0 sin omega t divided by n omega. And the other term is P is 0 cos omega t minus n omega x0 sin omega t. So you can see that this each expression contains two terms. So you can write it as a plus b and c plus d. So what is the commutation relation for this kind of problem? So this boils down to AC plus AD plus AC plus AD. So let's see, this is nothing but this is the A term, this is the B term, this C, and this is D. So let's see the individual terms. So AC is x0 cos omega t, and C is ps0 cos omega t. Then AD is the first term is this multiplied by C is 30 is minus m omega x plus 0 sin omega t. And the other term is B and C and commutation relation, which is A0 sin omega t divided by n omega, and C is cos omega t, and the last term is A0 sin omega t divided by x is 0. So you have to just separate out the individual terms so that you can simplify the overall expression. So let's see the first term, this one. So this one is you can see there is a cos omega t here, cos omega t here, and cos omega t you can take out from the computation relation because this is constant. So the resultant expression is 2 cos omega t is there. So when you multiply it, then it will be cos square omega t. So this is cos square omega t. And, so if you see the second expression, this one, so you see that there is a x term here cos omega t, and there is also a x term here sin omega t. So instead of so x commute with each other, right? If you take x with some function of x, then this would be 0. Only the main difference is the cos omega t here, and there is a sin omega t here. So this means the overall commutation relation should be 0 because there is no non-zero commutation relation here. So that means this term is 0, and the third term is PS0 sin omega t divided by n omega and PS0 cos omega t. So that means there is also a momentum operator here, and there is also momentum operator here. So they commute with each other. So that means, and there is also only the constant term is different here. So that means this commutation relation is also 0. Now let's see the third one. Third one is, you can see, fourth one, there is a momentum operator here and there is a position operator here. So their commutation relation would be non-zero. So let's write the resultant expression. So there is a minus here. So let's pick out the minus, and there is 1 divided by m omega here, and there is a m omega here. So they will, when you multiply it, then they will cancel with each other. So I am not writing that constant. The resultant will be is 0 and a is 0. The constant term is sin square omega t. So that means, and this is this is commutation relation of x with p, which is IH curve cos square omega t, and the second one is this is the commutation relation between p and h, p and x. So that means this is minus IH curve. So this will be minus plus IH curve sin square omega t, and this is nothing but IH curve sin square omega t plus cos square omega t. This all you know, this is 1. So this is IH curve. So that means the commutation relation of position operator in Heisenberg picture at time t with the momentum operator at the same time t is nothing but IH curve. So this is the answer for this question. So this is the second problem about the Schrodinger picture as well as the Heisenberg picture. So let's see the third question. So the third question is related to the second question. So let's see what is given to us. So it is asking, use the expression of problem 11 and find out the commutation relation of position and momentum operator at different time in the Heisenberg picture. So instead of same time, it is now asking about what will be the commutation relation in different time T1 and T2. So let's see. So it is asking about the commutation relation. Let's say we are measuring the position at time T1 and another operator, which is momentum operator at time T2. So now it is asking about what will be the value of this commutation relation at different time. So similar to the second problem, you just have, what you have to do is just put the expression and open up the commutation relation. Use the property of commutator. Use the property and solve the individual term so that you can get the final answer. So let's see. So ST is given to us. So let's see. It will be the expression for position operator at time T1. This is nothing but x is 0 cos omega T1 plus E is 0 by m omega sin omega T1. The expression for momentum operator at time T2 is E is 0 cos omega T2 plus minus m omega x is 0 sin omega T1. T2. Now just what you have to do is just put the expression in the commutation relation and solve it. T1, T2. Now you can take this terms, the first term, this one is A, this is A, this is C, this is D. So similar to the previous problem, you can write it. This commutation relation is x is 0 plus omega T1 is 0 cos omega T2 and A with D 0 sin omega T2 and D with C will be PH 0 omega sin omega T1 is 0 cos omega T2. The last term is plus 0 sin omega T1 sin omega x 0 sin omega T2. Now, if you see, let's see which terms cancel with each other. So now you can see, if you see this second term, then you see there is only position operator here, and there is also position operator here. And the constant term, they don't have any kind of commutation relation. The commutation relation of constant operator is zero. Constant is zero. So you see that in the second term, there is position operator here, there is also position operator here. That means this commutation relation would be zero because x is there here and now there is also x here. Now if you see the third term, in third term also there is a position operator, momentum operator here, and there is also momentum operator here. So that means this term would be also zero because P commute with P. So that means the resultant will be I want to ask one question. Do you want to repeat this question because you joined in the middle? Do you want me repeat or do you want me to continue the step? You can tell if you want me to repeat the question and the steps also. Okay. I'm not.
यस मैम रिपीट कर दीजिए.
Sorry. You want me to repeat the question?
यस मैम.
I am asking. You are unmuted. You can tell now. Anju.
यस मैम.
Your mic is unmuted. You can tell me now. Do you have any query or? Okay, let me repeat the question for you. Okay, so it is given that there are two. This condition is given to you. This is the expression for x is the position representation in the Heisenberg picture, and p is the position momentum representation in the Heisenberg picture. So this expression is given to you. Now it is asking about what will be the commutation relation of this position operator and this momentum operator at different time in the Heisenberg picture. Okay, so it is asking about will the commutation relation of this at different time T1 and T2. So what we have to do is just use this expression, this, and solve the commutation relation. Okay, so xt is given, so you can find out what is the expression for x t1, which is this one, and find out the expression for momentum operator in different time t2. So what you have to do is you have to just put this expression in the momentum in the commutation relation, and you are seeing that each of this representation x and use another color. So each of this representation have two terms. So what I've done is I have named the term one is A, this one is A, second is B, and for P it is C, first term, and it is D. So it is similar to, so if you want to find out what is the commutation relation of X and P at different time, so it is nothing but the commutation relation of A plus B and C plus D, right? So this is nothing but the if you have this kind of commutation relation AB plus CD, so this is nothing but this one, right? A with C, A with D, B with C, and B with D. So I have just used that property of commutation relation. Then what I have done is in the second step, I have just put the expression for A, B, C, D in the individual commutation relation. It is AC, the first term is commutation relation of AC, The second is commutation relation of A with T, and this one is P with C, and the last one is P with T. Now, if you see the AD term, like the second term, you are seeing that there is X here, there is X here. So X and X commute with each other. That means this commutation would be 0. Similarly, you are seeing that in this term, P is here, P is here, and T is here. So that means the commutation relation of this one is also 0. So only non-zero term is SC and BD. So let me write the expression for SC. This is the first term, P is 0, cos omega T2, and BD is P is 0, sin omega T divided by omega minus m omega x k 0 sin omega t. Right? Now, if you see the first one, the first expression, this one. So just these terms are constant at cos omega t1 and cos omega t2. So you can pick out, you can take out this constant term from the commutation relation. So the final is x is 0 and t is 0, and there is a constant term which is cos omega t1 to cos omega t2, right? And the second term is, in second term, there is a, you see there is a 1 by m omega here, and there is a m omega here. So when you take the commutation relation, then they will cancel with each other. This m omega, 1 by m omega and m omega. So the final term is t is 0 minus is 0. There is a constant term sin omega t1 and sin omega t2 that you can take out from the commutation relation. So this is sin omega t1, sin omega t2. So now you know this commutation relation. This is nothing but IH cut with cos omega t1, cos omega t2. And the second one is, this is also, there is a minus term here, so you can take out the minus term and write it here. So this means this is minus PS0, x is 0, sin omega t1 and sin omega t2. So this is nothing but minus IH cut. So the resultant expression is IH cut cos omega t1 cos omega t2 plus this minus minus plus IH cut sin omega t1 and sin omega 2. So that means this is nothing but cos omega t1 cos omega t2 plus sin omega t1 sin omega t2. So this is cos A cos B. This is nothing but cos A cos B plus sin A sin B, which is cos A minus B. So this is nothing but IH cut cos omega t1 minus omega t2. So the final expression is IH cut cos omega t1 minus t2. So the answer will be, there is no option. So answer, this is the answer. This is the final answer. So if you measure to the position and momentum operator at different time, then the commutation relation is given by this. Now, if you see in this expression, if you see in this expression, if T1 equal to T2, then it will be cos 0, which is nothing but 1. So that means if you measure this commutation relation at same time, like T1 equal to T2, then this will be IH coefficient. Okay, so this is the final answer. Let's see the fourth question. So before starting the fourth question, please go through the question once. So the fourth question is like this. The polymetric, the definition of spin half operator, which is SI equal to sigma I by 2h cut, R Hermitian, and F trace equal to 1. So it is asking whether this statement is true or false. So what is given to us? It is asking the polymetrics. So for spin of particle, the spin angular momentum is can be written as sigma I by 2h cut. So this spin angular momentum expression is not required for our problem here. So what is of interest here is this matrix sigma I, which is the polymetric. These are the polymetric. So these are the expression for the polymetrics. If you have 3 dimensions, then you have sigma x, sigma y, sigma z, which is sigma x you can also take it as sigma 1, sigma y as sigma 2, sigma z as sigma 3. So the expression for sigma s is the matrix represented is like this, is 0, 1, 1, 0. For sigma I, sigma y, it is 0, minus I 0. And the for sigma z, it is nothing but 1, 0, 0, minus 1. Now, if you see this sigma x, sigma y, and sigma z, so if you take the dagger of this sigma x or sigma y dagger or sigma z dagger, so you will see that these are Hermitian. Hermitian, you can, I think, you can find out how to find out the Hermitian of a dagger of a matrix. This is nothing but the transpose of this matrix with complex conjugate. Right? So if I take this sigma, let me so for the dagger for the sigma one of the matrix. So for sigma is if you take the dagger of this matrix, then it is nothing but 0, 1, 1, 0. If you now take the complex conjugate, it is 0, 1, 1, 0, right? So that means sigma, this is nothing but this is sigma x dagger is equal to sigma x. So this is Hermitian. Now if you follow the same step, if you dagger, find out the transpose and complex conjugate, you will see that this is nothing but sigma y, similar to sigma z also. This is nothing but equal to sigma z. So that means the Pauli matrices are these are Hermitian. But now if you see the trace of this matrix, right? Trace means what? Trace means the summation. The trace of a matrix is nothing but summation of diagonal elements, right? These are the summation of diagonal elements. Now the matrix is already given to you. You just have to see the diagonal elements and find out what is the summation. So if you see the sigma x, the diagonal element is 0, 0. That means sigma x trace is 0. Now for the sigma y, it is also 0, 0. The trace is also 0 here. And for the sigma z also it is 1 and this is minus 1. So that means the trace is also 0 here. So this conclude that the trace of this Pauli matrices are zero and they are Hermitian. But what is given to us in the statement is given that these Pauli matrices are Hermitian as well as they have trace equal to 1. So this condition is not true. Trace is not equal to 1. Trace is 0. That means the answer is false. So the Pauli matrices have trace 0 and they are Hermitian. These are some of the property of Pauli matrix. Now, question. So during solving this question, if you have doubt in any kind, any step, so please feel free to stop me there and ask, ask your doubt. I can solve in at that time only. So let's see our next question. So next question is the eigenvalues of his spin-off system described by Hamiltonian. So spin-off system is there and the Hamiltonian is by AI plus B sigma 2. Now it is asking about what will be the eigenvalues of this Hamiltonian operator. So I think this one is easy. Here I is nothing but the identity matrix, which is 1, 0, 0, 1. So you have to just write the operator in matrix form and find out its eigenvalue using the same process that I have described in my previous videos. Now this is B, which is nothing. Sorry. And it is also given that AB are real positive constant and sigma 2 is the Pauli matrix, which is nothing but sigma 1. So sigma is nothing but 0. I think this one is minus I. So this is sigma y matrix, Pauli matrix in z direction. So the whole expression would be this A minus BI, AI, A. So this is the matrix for the Hamiltonian that is given to us. So to find out the eigenvalues, what you have to do? You have to just solve this equation, which is determinant of h minus lambda I equal to 0, where lambda is the eigenvalue. It's the determinant of A minus lambda is minus bi, A minus lambda equal to 0. So determinant is nothing but this cross this minus this cross this. So this is A minus lambda square plus, okay, this is minus bi equal to 0. So this is A minus lambda square. I square is minus 1. So this is minus b square equal to 0. So this is nothing but a square minus b square. Which you know this is a minus b plus a plus. So this is a minus lambda minus b, a minus lambda plus b equal to 0. So that means this individual term is 0 because the right hand side is 0 and this is multiplication of two non-zero quantity. So that means A minus lambda b equal to 0, which gives lambda equal to A minus b. The second term is 0, which gives lambda equal to A plus. So these are the eigenvalues of this Hamiltonian operator. So what you got? You got the eigenvalues lambda is either A plus b or A minus b. So the answer will be B, which is a plus b and a minus b. Right? So let's see our next question. So, do you have any doubt for the problems I have solved now? If not, then I can continue solving the next problem. So let's see our next problem. So is given an operator A representing observable A as two normalized eigengates psi1 and psi2 with eigenvalues a1 and a2. So what is given? Is given an operator A, and it is given that the eigenvalues of these operators are a1 and a2 with eigengates psi1 and psi2 for a2. And also another operator B representing observable B has two normalized eigengates phi1 and phi2 with eigenvalues b1 and b2 respectively. So what is also given? Given another operator B, their eigenvalues of this operator is b1 and b2 with eigengate phi1 and phi2. This is given. These two different operators are given. Now it is also given that the relation between this eigengate. If the psi1 is related to phi1 and phi2 with 1 by 5, phi1 plus 4 phi2 and psi2 is 1 by 5, 4 phi1 and 3 phi2. This is given the relation between this eigengate. Now it is telling if the system is in the state psi1 and then observable B is measured, then what is the probability of measuring B? So it is given the state is in the eigengate psi1 and we act the operator on it. So it is asking about what is the probability of getting B1 here. After the measurement, what is the probability of getting B1? So whenever this kind of question is asked, so first see what is the observable acting on the initial gate. So initial gate is psi1 and B is so what your first thing what you have to do is express this psi1 in terms of the eigengates of the operator acting on it, which is B, and the eigengates of B is nothing but phi1 and phi2. So your first job, your first thing what you have to do is express this initial gate in terms of this phi1 and phi2, which is already given. This is already given, nothing but 1 by 5, 3 phi1 and 4 phi2. So the expression is given to us. Now it is asking what is the probability of getting B1. So for that, what you have to see is you have to see what is the eigengate that is related to B1. So eigengate related to B1 is nothing but phi1, right? So the probability of getting B1 then probability of getting B1 in the measurement is nothing but the probability of getting the state phi1 after measurement. So this is equal to the probability of getting phi1 is nothing but phi1 with the initial gate psi inner product square divided by psi phi. This is the postulates of quantum mechanics. I have used this postulate. So if you see psi, this is inner product. So this one is psi 1. If you take the inner product of psi 1, it is nothing but 3/5 square plus 4/5 square. So that means this is 1. So it is already normalized. So you can take this denominator as 1. So what we left with probability of getting phi 1 is nothing but psi 1 square. So the inner product of phi 1 with psi 1 is nothing but, so this is here. So if you ask phi 1, then only this term is non-zero. This term will become 0 because phi 1 and phi 2 are orthonormal cases. So that means phi 1 with psi 1 inner product is 3/5. So the probability of getting phi 1 is nothing but 3/5 square is 9/25. Similarly, you can also check probability of getting phi 2, which is probability of getting eigenvalue of p2 is nothing 4/5 square is 16/25. So the answer will be 9/25, which is answer B. So in this kind of problems, when they are asking about eigenvalue, what is the probability? So just what you have to do is first express the initial gate in terms of the eigengates of the observable, which is acting on this state. Then find out what is the eigenvector corresponding to this eigenvalue. From that, you can find out what is the probability of getting that eigenvector. Okay. So let's see our second next problem. So this problem is based on Heisenberg picture and Schrodinger picture. Is given to us. It is given to us as given to us is P, Q, and R are operators in the Schrodinger equation satisfying relation PQ equal to R. So it is given P, Q are operator in the Schrodinger picture and they have commutation relation which is equal to R. Okay. Now it is asking then what is the commutation relation of the corresponding operator PH, QH, RH of the Heisenberg picture. But is asking what will be the commutation relation in the of the same operator in the Heisenberg picture. So one thing in the Schrodinger picture is given to you. Now it is asking about what will be the expression or the commutation relation in the Heisenberg picture. So let's see. So you know that in the Schrodinger picture, the state evolves. The operator remains constant, but the state evolves. But in the Heisenberg picture, what we say, the operator evolve in time, the state remains same. So if we have operator P in the Schrodinger picture, so in the Heisenberg picture, we take the operator P is e to power 5 h p by h code P in the Schrodinger picture and e to power minus I h p by h code. Similarly, if we have operator Q, then We'll write the same operator in the Heisenberg picture is e to the IH TYH per QH, sorry, not QH, is the operator in the Schrodinger picture into the minus IH TYH per, and the third one equals operator R. So now we write in this Heisenberg picture is e to the IH TYH per R e to the minus IH TYH per, right? So what is given to us is we are given the commutation relation in the Schrodinger picture is P equal to R. So let us solve this commutation relation. So this is nothing but PQ minus QP equal to R. Now you know that if you take this kind of operator, e to minus IH squared multiplied by e to the IH t by h squared. So this is nothing but the identity operator, right? So you can incorporate this expression here. So this is nothing but P multiplied by identity. So it's like incorporating a identity matrix here. E equal to R. So this is P e to the minus IH t by h squared e to the IH t by h squared Q minus Q e to the minus IH t by h squared e to the IH t by h squared P equal to R. So now to get the expression for the Heisenberg picture, what you have to do is you have to just multiply a term here. Multiply term e to the IH t by h squared here, and you have to multiply a term e to the minus IH squared t by h, so that the final expression is similar to RH. So you have to multiply these two terms in both sides, so that the expression doesn't change even after the multiplication. So what I've done is I have multiplied IH TYH squared with the expression this total term. Let's see, this is D, so this is D, and I have post multiplied e to minus IH TYH squared. Then this is equal to e to the IH TYH squared R e to the minus IH TYH. Right? So this is nothing but RH. Now let's see what is the left hand side equation. So in left hand side we have e to the IH TYH squared. Let's see what is the terms for D. So one term is P1, P e to the IH T by H squared e to the IH. So I'm just writing the expression for D and I'm multiplying this term, the first term as well as the second term. So after this Q, we have this one. This IH T by H squared. Now the second term is this one. So we have to multiply one here and we have to multiply this one here. So this expression is e to the IH T by H squared Q e to the power minus e to the IH T by H squared P And there is a term e to the minus RH dy h square, which is equal to RH. Now, if you see this term, this is nothing but pH, right? And this term is nothing but QH. Similarly, this term is QH, and this term is pH. So the final expression is pH multiplied by QH minus QH multiplied by pH equal to I. Which is nothing but the commutation relation of pH to QH or RH. Okay. So what you've seen, so you were given P equal to R, then in the Heisenberg, this is in the story picture. Then if you have to find out what is the expression for the same commutation relation in the Heisenberg picture, then this is nothing but pH QH equal to RH. Right? So if I take one example, so let's see. You know that in the Heisenberg picture, the commutation relation of x with p equal to IH squared x with px, right? X with py is anyhow 0. Is 0 x with py, x with pz. Only x with px is non-zero. So that means if you have this condition and if you want to find out what is the expression for the commutation relation in the Heisenberg picture, so this is nothing but xh is RH, which is nothing but IH squared. Okay, if you have same time, then you will find it is IH squared. Then if you are have different time, then as I said, as I solved in one of the question, then this is nothing but IH squared cos omega Q1 minus K2. Okay, so this is how you can solve the commutation relation. Like if you can use this property like I have incorporated this identity operator here so that you can relate it to the Heisenberg picture. So you can use this small tricks to find out your answer. I think this question is clear to you. Let's see our next question. So go through the question once. So this is based on the commutation relation. Okay, so this is based on commutation relation. So let's see what is given to us. So it is given, consider the operator alpha, which is equal to x plus d by dx acting on a smooth function of x. Then what is the commutator of alpha with cos? So it is telling, it is given that alpha equal to x plus d by dx, and it is asking about what will be the commutation relation of this kind of commutation relation. So what will be the value for this commutation relation? Okay, so if this kind of problem is given, so what you have to do is you have to act this commutation relation on a normal eigenkit, which is here you can see the operator is a function of x. So it's better to act it on a function which is also a function of x. Okay, let's say psi of x. So now what you have to do is just use the property of commutation relation. So this is nothing but alpha cos x minus cos x alpha, right? Acting on psi of x. So before solving this, you can see, let's solve this one first. So the alpha cos x is nothing but x plus acting on a sun. I forgot to write the state. Normalized case, sorry, not normal case. So this is nothing but alpha x cos x is psi of x, and this is x plus dy dx cos x psi of x. Now you use the property of commutator. So this is nothing but if you have this kind of, then the commutation relation is this one with this and this one with this. So this is x cos x plus dy dx cos x commutation relation. There is a psi of x here, right? Now you see that this is nothing but there is a x here and there is a function of x here which is cos x. So you know that if there is a function is operator is given and another function is given which is also a function of the same operator. So this is nothing but 0, right? If you have same kind of function in either side, then this is 0. Here x and there is a cos x here. So this means this first term is 0. So what you have left with is the second term, which is dy dx cos x psi of. So now let's solve this commutation. This is nothing but dy dx cos x minus cos x dy dx with psi of x. So this is nothing but dy dx of cos x psi x minus cos x dy dx of psi of x. So use the property of derivative. So this is nothing but this whole term is dy dx cos x multiplied by psi of x plus cos x and derivative of psi of x. So the last term is cos x dy dx of. So this term will cancel, right? This is plus and this is minus. So they will cancel. So the only last term is this one. So derivative of cos x is nothing but minus sin x and this is psi of x. So what you got is, you got when alpha cos x, when it relation act on is generalized state psi of x, then you got minus sin of x with psi of x. That means the commutation relation of alpha with cos x, nothing but minus sin of x. Okay. So this is the final answer. So similar to this problem, for any kind of other commutation relation, you just have to follow the same steps, and so that you can get the answer for any kind of uh, operator. So the answer is minus sin x, which is a. Okay. So just follow. First, what you have to do, you have to act normal gate here. Then you have to solve this expression and use the property of commutation relation. Then solve the final expression. Then you will get the expression like this. Okay, I think this problem is clear to you. So if you have any doubt, then you can ask me. Otherwise, I will proceed to the next question.
नो मैम, कोई भी डाउट नहीं है।
Okay. So let's see our next problem. So the next problem is based on the postulates of quantum mechanics. Okay. So let me read out the question for you. It is given in a system described by three orthonormal bases. So we are given three orthonormal bases, just 1, 2, and 3. And there is one operator, the operator A. The operator, if there is an operator A, and we have written this operator in terms of this orthonormal basis is A equal to 2, 1, 1, there is 3, 2, 2, minus 3 with. So this is given to you, the operator expression in the orthonormal basis. Now it is asking the possible measurable values of this observable A will be. So what is the possible measurable values of A? So any kind of experiment that we do in quantum mechanics, the possible measurable values of any operator A is nothing but the eigenvalues of A. So if you know the eigenvalues, then these are nothing but the results that you will get after conducting one experiment. So your main task in this problem is to find out the eigenvalues of operator A. So for that, what you have to do, you have to express this operator in terms of matrix, right? So the matrix, I think you can write. There are three orthonormal bases, so you will get 3 cross 3 matrix. So I will just write out the matrix equation, matrix form. So if you have orthonormal bases 1, 2, and 3, so what is the matrix? How can you find out the matrix element? So this is nothing but 1, A1, then 1, A2, then 1, A3. Similarly, 2A1, 2A2, and 2A3. The last one is 3A1, 3A2, and 3A. This is how you can find out the matrix. So you are given A, which is equal to 2, 1, 1, 2, plus 3, 2, 2. We see what is the given 3, 2, 2, and last one is 3, 3. So what you have to do, you have to find out each term, right? So let me. So the first term is 1 with 1. So 1 with 1 will give a non-zero quantity here. So that means A1 equal to 2. Similarly, If you want to find out 1 with 2, the second term, then you have to look for one operator, which is 1, 2 kind of expression. So in this expression, you are seeing that only 1, 1 is there. This is 1, 1. Then there is also 2, 2 is here and 3, 3 is there, right? That means only the non-zero quantity will be 1, A1, 2, A2, and 3, A3. Because only that quantity will be non-zero and the other terms will be 0. Because this A operator don't have any cross talks. Okay, so that means your A matrix will be 1 A1. This one is nothing but 2 and 2A2. 2A2 we will get here. Get 2A2 here. So you will get 3. I think this one is not visible. Let me write it again to 3 and 3A3. You will get here. So this is 1. So other terms are 0. Okay. So if
Minus
you
1.
like diagonal matrix, so the you have matrix like this, then the eigenvalues are nothing but the diagonal elements.
मैम -1 आएगा या +1?
Eigenvalues are diagonal elements, which is 2, 3, and 1. So if you have a diagonal matrix, then you don't have to solve this equation, like the equation that we solve determinant of A minus lambda equal to 0. You don't have to solve this equation. You just have to take what is the diagonal elements, which is 2, 3, and 1. These are the eigenvalues. So that means for this matrix, eigenvalues are 2, 3, and it is, oh, sorry, there is a -1 here, right? -1, 3, 3. So that means if you take 3 with 3, then this will be -1. Because there is a -1, minus here, minus sign. So diagonal elements is 2, 3, -1. So that means the possible measurable values of this observable are nothing but the eigenvalues. And because these matrices are diagonal, so you can take the diagonal elements as the eigenvalue. So that means the answer is 2, 3, -1, which is A here. Okay. So this is based on the eigenvalue equation. Let's see our next problem. So the next problem is also based on eigenvalues and eigenvectors. Okay. And here options are also given, and you can see the options are different. Right? The eigenvalues are different in each of these options. That means if you find out what is the eigenvalue, then you can easily know what is the answer to this given question. You don't have to calculate eigenvector, but if there is a question instead of eigenvalue, they're asking about eigenvector, then in that case, you have to find out what is the eigenvector of this matrix. So I will solve both eigenvalue and eigenvector so that you can find out how to get the eigenvalues as well as eigenvectors for a Hamiltonian like this. So let's see our problem. So it is given the Hamiltonian operator for a two-state system is given by this. It is given what is a two-state system. So the Hamiltonian is given by A 1 1 -2 1, 2, and then 2 with 1. Where A is the number which with the dimension of energy, and the corresponding eigenvalues and eigenvectors will be. So first what you have to do, you have to express this Hamiltonian operator in terms of matrix. So it is a, you can see there, this is a two-state system, only the orthonormal bases are 1 and 2. That means we will get a 2 cross 2 matrix. So H is nothing but H matrix is 1, H1, then 1, H2, then 2, H1, and 2, H2. Right? So let's see what is the expression for H. H is nothing but 1 with 1, 2 with 1, 2, and 2, 1. So that means there is a 1 term here, right? So that means 1H1 is A. Then there is a 1, 2 term here. So that means 1H2 equal to nothing but the coefficient which is minus 2A. And there is a 2, 1 here. So that means 2H1 is nothing but minus A. So the other term which is, you see there is no 2, 2. This kind of expression, that means 2H2 equal to 0. So the final matrix equation is nothing but 1H1 which is A, then 1 is 2 minus 2A minus A and 0. This is a simple matrix. You can easily find out the eigenvalue. So just solve this equation, determinant of H minus lambda equal to 0. That means determinant of A minus lambda is minus 2A, and this is A, and this is minus lambda equal to 0. So that means this is minus lambda, A minus lambda, and there is minus 2A square equal to 0. So this is nothing but lambda square minus A lambda minus 2A square equal to 0. So you have to just find out what is the solution for this polynomial equation, which is nothing but minus b plus or minus root over b square minus 4ac, b square minus b plus or minus root over b square minus 4ac by 2a. So if you solve this, then you will get lambda equal to either 2a or minus a. So these are the eigenvalues we will get. So let's see the options. So you can see there is a 2a minus a here. That means the answer is this. You already found out the answer. What is the answer to this question? So you don't need to find out what is the eigenvalue, vectors for this operator. But for the sake of completeness, I will show you how to find out the eigenvector. So I think there is a term missing here. There will be root over 5 here, and there will be root over 5 here. Okay. So let's see how to find out what is the eigenvector when the eigenvalue is 2a. And for minus it, that you can find out by following the same step. So for that, let's take phi 1 is the eigenkate. Then that means whichever eigenvalue lambda equal to 2a. So that means h phi 1 equal to lambda phi 1. So what is h? H is nothing but a minus 2a minus a and 0. Let's take phi 1 is some unknown terms. Let's say take C1, C2. So this is C1, C2, and lambda is 2a, C1, C2, right? Now, if you see in the second term, there is a 0 here. So first solve this one. So this will give a minus a C1 equal to 2a C2, right? That means C1 equal to minus of 2 C2. So that means the eigenvector phi 1 is nothing but C1 C2, which is C1. C1 is nothing but minus 2 C2, and this is C2. Now, if you normalize it, then you will get phi 1 equal to. So normalizing by means you have to divide it by its norm, which is phi 1 phi. Okay. So then if you normalize it, then you will get 1 by root over 5 minus 2 and 1. So this is one of the eigengate which is corresponding to lambda equal to 2a. So how can you write it in terms of, this is the matrix equation, right? So you have to write it in terms of Dirac form. So you can write phi 1 is, this is nothing but, if you want to write it in terms of Dirac, what is the procedure? It is nothing but Cn with the orthonormal basis, which is 1 or 2 here, right? Cn with n, C1 with 1, with C2 with 2. C1 is nothing but 1 with phi 1, and C2 is nothing but 2 with phi 2. So 1 with phi 1 is nothing but, if you see this matrix equation. So phi 1 matrix you got is minus 2 by root over of 5 and 1 by root over of 5. So these are nothing but 1 with phi 1, the first term, and 2 with phi 2. So just put this C1, C2, which is C1 is root over 5. This is 1 by root over 5, right? So that means phi 1 is nothing but minus 2 by root over 5, 1 plus 1 by root over 5. So this is how you can find out the eigenvector, and you can write it in terms of Dirac equation. Okay. So if you see, then you will see that there is this, we have calculated this one. So for lambda equal to minus a, you can follow the same process and you will get the eigenvector is nothing but 1 by root of 5, 1 and 2, 1 plus 2. So this is how you have to proceed for eigenvalue and eigenvector. Okay. So the eigenvalue you got is 2a and minus a. This is the eigenvalue, and this is the eigenvector that we got for lambda equal to 2. And the next one, lambda equal to minus a, you can follow the same step and calculate it. Okay, I'm leaving this to you to calculate. So let's see our next problem. Next problem is easy. So you have to just find out the probability based on the probability result. So let's see what is given to us. So it is given the particle is in a state Q. So the particle is in a state Q, which is 1 by root over 50 4 1 minus 3i 2 plus root over 5 3. So this is given to you. So 1 minute. So this is given, and 1, 2, 3 are autonomous bases. Now in this state, we are measuring an observable, which is B. Okay, we are acting B on its state. So B is given as A 1 1 plus B 3 3. Okay, now it is asking the probability of measuring B in such state. So, so it is asking when you are to be on this state Q, then what is the probability of getting B here after the measurement? So as I told, what you have to do is first we have to express this state in terms of this eigenvalues and eigenkets of B. Okay, the operator that is acting on it. And this is already given. You don't have to find out. Already in the question it is given. I am telling you because if there is a situation, if it was not given, then you have to be careful in that situation. For this case, it is given. So let's see. So B is given A 1 1 plus B 3 1. Right? So let's see the let's find out what is the matrix equation. So B, you see, there are 3 orthogonal bases. Then you will see 3 cross 3 matrix, and you are seeing that there is 1 1 term here and 3 3 term here. So that means 1B 1 is non-zero and 3B is non-zero. So this is A, this is B, and other terms are 0. Right? So that means this is also a diagonal matrix. So that means eigenvalues are nothing but the diagonal elements, which is A here and B here. So eigenvalues are A and B. So eigenvalues you have found out. Now what you have to do, it is asking what is the probability of getting B here. So that means what is the probability of getting the state, the eigengate that is related to this eigenvalue B. So how can you find out what is the eigengate of A eigenvalue and B eigenvalue? So for that, you can see B is written as 1, A plus B 3 3. So now if you act 1 B on 1, then you will see you will get A, and if you ask B on 3, then you will see B. So that means A is the eigenvalue and eigengate is 1, and B is the eigenvalue and the corresponding eigengate is 3. So that means B eigenvalue eigengate is 3. So the probability of getting B is same as probability of getting the state B after the measurement. Now use the postulates of probability of finding a state, which is if 3 is given, then probability of getting 3 is nothing but 3 with initial state vector, which is Q square divided by Qp. Right? This is how you can find out the probability. So if you see Q, so QQ is here. So if you find out just take the inner product of q with q, then you will see this is 1. So that means this is already normalized. So you can take the denominator as 1. So probability of getting B is nothing but only 3q squared. Now the inner product of C with Q is nothing but, if you see this term, so only this term is non-zero, right? This will give a non-zero 3 equal to 1 and the other terms are 0. The coefficient is root over of 5 divided by 30. So that means this is nothing but root over by 30 square is uh, 6. So this is 1 by 6. 1 by root over 6 square divided 1 by 6. So the probability of getting the value B here is 1 by 6. Now if the question, if in the question, if they have asked what is the probability of getting A. So for that what you have to do is, if instead of B, they are asking about A, then first see what is the eigengate related to A, which is nothing but 1. So if you see this expression, then it is, sorry, this is not the full eigen, there will be 1 here also, there is 1 here, right? Sorry, 3 here. Because I have wrongly read, if you ask B on 1, then B is this, then it will give A 1 with 1, 1. So this is 1, so this is nothing but A1, where B with 3, it will be 3, 3, and 3. This will be B with 3. Right? There is a K here also. I forgot to write it. So if you see this expression, this is the eigenvalue equation. You see that the eigengate of A is 1. So if you want to find out what is the probability of getting A, that means this is nothing but 1q squared. Right? So 1q square is, first see what is the expression for q. So only this term will give non-zero quantity. This term. So and the coefficient is 4 by root over 30. So that means you will get probability 4 by root over 30 square, which is 16 by 30. Okay. So this is the probability of getting, probability of calculating A and B. So let's see our next problem. So the next problem is based on the commutation relation also, and it is, let's see the problem first. So it is given LM with commutation relation of LZ with A is 0. Then for any observable A, it is given this relation Z A with LM. This is 0. Okay, this is 0 for any observable A. Okay, this is valid for any kind of observable. The observable may be a position position operator, may be other operator like Lx, Ly, L square. So first we have to see what is asking in the question. So it is asking the then the expectation value of Py. It is asking about what is the expectation value of Py. What is this? This is given to you, this condition, right? So you know that one of the expression of, if you have, if A equal to, let's say, if A is Px, you know that this is nothing but IH cut Py, right? It is given that this condition is valid for any kind of observable A, so I have taken the observable A equal to Px. So how can you find out this form? You just have to use the expression for Lz, which is Py minus y Px, Px. So use the property of commutation relation, and then you can find out that this is nothing but IH squared P. Okay, so that means this condition Lz with Px. If I have taken the operator A is Px, then it is also 0, right? So that means Lm with this is IH squared Py. Lm, this is 0. So that means IH squared Lm with Py Lm equal to 0. That means this is nothing but the expectation value of Py, right? Expectation value of Py. So that means expectation value of Py is 0. So that means the answer is 0 here. Okay. So let's see our next problem. So the next problem is like this. So for a, it is given for a particle subjected to the potential C is equal to kx square. We are given a potential Vx equal to kx square plus a x to power 6, where A is a positive. Then it is saying we expect energy eigenfunction to become dz. So it is a statement is given. Now it is asking whether the statement is true or false. So what is given? It is given the particle is in this potential, which is a 1D potential, right? It's a function of x only. So it is a 1D potential. Now it is telling that in this kind of potential, the energy eigenfunction functions are degenerate. So it is asking whether in this potential, energy eigenfunction is degenerate. Okay, but you know that if you are given a 1D problem, 1D potential, then all the energy eigenfunction, they are non-degenerate. They are not degenerate. For 1D problem, there is no degeneracy. All states are non-degenerate. If you have 2D, 3D problem, then in that case, the degeneracy appears. So that means this statement is false. So energy eigenfunctions are not degenerate, they are non-degenerate. Okay. So this is false. The answer is B. This is one of the conceptual problems. Okay. So let's see our next problem. So the next problem is based on the commutation relation. It is asking, we are given two operators Lz, another one is P square x. So what it is asking, what is the commutative bracket of this relation? Okay, this 1 by IH squared LZ P square. What is this expression? So this is easy. You just have to use the property of commutator, right? So we have to just open up this bracket and write individual terms. So this is nothing but if you write it, so this is LZ P square x minus P square x LZ, right? So you know the commutation relation of so what you have to do is you have to write it in terms of commutation of relation of two operators. So nothing but if LZ P square x, what I will do is I will add one term which is P square LZ. Okay. And to cancel it, I will add another term. Similarly, there is a term P square x LZ here. Okay. So this is nothing but IH cut. If you see, this is nothing but the commutation relation of LZ with the P square, okay, plus there is XLZ here, LZX, and there is XLZ here. This is P square and commutation relation of LZ with X. So your main task is find out what is the commutation relation, what is the value for this commutation relation. So let's see, I will tell you how to proceed. So P square is nothing but Px square plus Dy square plus Pz square. So that means this is Lz Px square plus Lz Py square plus Lz Pz square. So now what you have to do is you have to use the expression for Lz. Lz is nothing but xpy minus ypx, right? So you have to use this and put this Lz in each term. Then what you will find out now? You will find out each commutation relation is 0. So that means Lz with P square, these all terms will vanish. Okay, that means Lz commute with P square. Okay, so this is 0. So the first term is 0. Now see the second. Now let's see the second term, which is Lz with X. So similarly, we have to use the expression for Lz, which is xpy minus yp xp. Solve it. If we solve it, then we will get I squared y. Okay, so that means this I squared y, the second term. That means what is given to us? That means 1 by I squared Lz P square x equal to 1 by I squared P square I squared y. I squared I squared will cancel. We will have P square y. The answer will be D. So this is based on commutation relation. Now let's see the other problems. See what I can solve. Our question left. So let me solve this question. Okay. So this will be the last question that I will be solving. Please go through the question one. What is given? So it is based on the Schrodinger picture and Heisenberg picture. So let me solve the problem. It is given a particle of mass m is in a potential d equal to half m omega square x square, where omega is a constant. Now it is given an operator A which is equal to root over of m omega by 2h squared xk plus ip by m omega. It is given. Now it is asking in the Heisenberg picture, what is the expression for dA by dt? But it is asking about what is the change of this A operator with respect to time. So in the Heisenberg picture, the time of evolution of a operator is A is given by this form. This is nothing but IH curve, commutation of A with H plus tau A by tau T. So this is the expression for time evolution in the Heisenberg picture. Okay. So now it is given the expression for A is like this. So you are saying that there is no explicit time part here. There is no term for T here. So that means dou A by dou T equal to 0. Okay. So dou A by dou T is 0. So what we are left with A by dt of A is nothing but 1 by IH dot commutation relation of A with H. So now this is all about finding out the commutation relation of A with H. So just let's put the individual expression and where is the X plus IP by M omega with H. So this one is a constant, so you can take out from the bracket by 2h squared. X IP by M omega with H. So what is H here? So H is nothing but E square by 2m plus the potential. So potential is half m omega square x square. So that means dou A by dou T is 1 by I squared root over of m omega by 2h squared x plus IP by m omega. This term is p square by 2m plus half m omega square x square. Right? So this is for this we have to just use the property of commutation. In write it as one is A, one is C, one is T. So the commutation relation of this is A with C, X A square by 2 A with B plus x half omega square x square A with C by 3 by m omega A square by 2 plus B with D by 3 by m omega half m omega square. So there are total 4 terms. Now, if you see some of the terms as 0 because here x operator is x, here also operator is x. So this means this term is 0, and this is also there is operator p and p. That means this is 0. So only 2 non-zero terms are there. Let's see what is the non-zero term, which is the first non-zero term is x with b square by 12. Okay. So now if you solve it, this is nothing but x with x square by 12. 1 by 2 is a constant, so I can take it out. This is x with px square, right? So this is nothing but this one is 2 I h cut px. To use the property of commutation relation, find out the commutation of x with px square. So this means this is nothing but 1 by 2 divided by 2 a square px. So this will be h square px by 10. Now see, let's see the second term, which is I 3 by n omega half omega square x square. So first, let's take out the constant terms. This is n omega square 2 I here n omega. The remaining is p. You can write p as px. So this is x square. Now same, use the property of commutation. Then you will find out what this is nothing but minus 2i square. Okay. So that means we will cancel omega. We will cancel this 2 here. The resultant will be h square omega. Now put these terms here. So that means we will get a by 2 equal to 1 by I h square together omega by divided by 2 h square. There will be I h square 6 by omega h square x. So what you have to do is you have to just take out this omega h square. This is x. This is I x divided by right. So now if you compare it to the a given here, then you will see that this is nothing but minus I omega, where a is given the question is of m root over of m omega by 2 h cut x plus ip by m. Okay. So this is how you can find out the time evolution of any kind of operator in a Heisenberg picture. So what you have to do is we have to use this formula. d by dt equal to 1 by I squared, A with H Hamiltonian and dou A by dou T. So use this and solve the commutation relation, then you will easily find out what is the expression for the time evolution. So let me stop here. In the next class, I will solve some more problems on hydrogen atom, then Heisenberg picture. So for now, let me stop here. And so I hope all the problems are clear to you. And thank you for joining the section. So let's meet on next Saturday on the same time, 6 to 8. So thank you all.